Hello everyone, welcome to Brain Blitz Audios. Today, in this episode of Mind Maps, we'll be dealing with wave optics. This is the 10th chapter in the grade 12 syllabus for physics in CBSE. And this is a very important chapter, and so therefore we have enlisted the help of this mind map in order to explain the chapter. Mind maps are easy tools for last-minute preparation of subjects and chapters. However, like this one, they can be very extensive, and therefore this video is devoted to explaining this mind map in a little bit of detail. So, today, our chapter is wave optics. Throughout our studies in our previous grades, we've considered light as a ray, but in reality, it is actually an electromagnetic wave of small wavelength. So, the earlier thought that scientists had was, if it was a wave, why didn't it bend around objects like sound? Well, the reason is that the bending effect is actually dependent on the wavelength, and since light has very small wavelength, it only bends around objects which are of comparable size. So therefore, when you have larger objects, then light does not bend. It acts as a ray. So the wave theory was able to explain a lot of phenomenon such as interference, diffraction, etc. So in this chapter, we're essentially going to deal with the main principle that is behind the wave theory of light, and we'll be looking at the properties that the wave theory explains, such as interference, diffraction, polarization, resolving power, etc. So, without further ado, let's move to our first topic. How can you consider light as a wave? Earlier, scientists like Newton and others proposed that light traveled as corpuscles in straight lines. But they could not explain properties like diffraction. Like Newton himself has said that diffraction was detrimental to his theories. And he was a great experimenter, so he recorded that down as well. Now, another contemporary scientist, that is Christiaan Huygens, he proposed the wave theory. Christiaan Huygens says that each point on the primary wavefront is the source of a secondary wavelength. So what essentially he said is that light acts as a wave. So light is an electromagnetic wave. And when light is a wave, it forms these fronts where all the radiation are in the same phase, called wavefront. And in these wavefronts, what happens is that we form secondary wavefronts. Since this is a circular, this is a point object, I'll be using circular wavefronts, and something like this. And then the tangents of all these circles will give you a secondary wave front. the next wavefront. So this is kind of, skewed out, but this is the general idea behind how the wave theory works, how Huygens' principle works. And in Huygens' principle, the point source generally has a spherical wavefront, while a line source will have a cylindrical wavefront. And if you want to have a plane wavefront like this one, then what you essentially do is you take the light source at a very far distance off. And from here you can use the spherical secondary wavelets, and then using the tangents, you can form a new plane wavefront. Now, in the wave theory of light, earlier we proved using the rays that the light refracts as well as reflects. Using a plane wavefront, we can actually prove the laws of diffraction, not diffraction, refraction and reflection. So we'll be able to prove these using the Huygens principle. Now, a wavefront, as we said, is the locus of all the particles vibrating in the same phase. So all of the energy vibrating in the same phase is called a wavefront. Now, the proof that light was an electromagnetic wave was also given by Maxwell and also Thomas Young with his experiments, but more on that later. For a spherical wavelength like this one with radius r, the intensity of light, I, is inversely proportional to the square of the radius, and the amplitude A is inversely proportional to r. So these are the two relations with respect to spherical wavefronts, and these are important because we'll be using them for our other studies on diffraction and interference. Now that we've studied the main theory behind how we can consider light as a wave, let's look at some of its phenomena that proves that light is a wave. First of all, we have interference. Interference was the phenomenon which Thomas Young used to prove that light was a wave. Now, this is the phenomenon in which two waves superpose to form a resultant wave. So two waves, they superimpose in order to form a resultant wave with either greater amplitude or lower amplitude. Here they use the superposition principle, which means that when you have two or more waves coming together, the resultant will be the sum of those two waves. For finding the intensity, we use the formula root of I1 plus root of I2, the whole square, is equal to I. Now we can write that as beta times A1 plus A2, the whole square. So since I is proportional to 1 by r square and A is proportional to 1 by r, so we can use the same formula. So we just remove 1 by r out and then put that under beta or something. So that is how we can find out that I is equal to beta times A1 plus A2, the whole square. A1 is the intensity of the first wave, A2 is the A1 is the amplitude of the first wave, A2 is the amplitude of the second wave. Now in interference, you can either have greater values or lesser values. Now the phenomenon in which you get greater intensity and greater amplitude is what we call constructive interference. So these two waves, they combine together and they form the resultant wave, which is greater than the two waves combined. So for constructive interference, we get more intensity. Now in this case, the total amplitude is the sum of both the amplitudes of both waves. For destructive interference, however, it's the exact opposite. You get darker spots. Darker spots and darker fringes are achieved when you see destructive interference. So both the waves, they join together, but then they cancel each other out. In constructive interference, they both are similar in phase. In destructive interference, it is something more like this. So they cancel each other out. Now, Thomas Young, in order to prove the wave theory of light, he decided to use a very special setup that we today know as the Young's double slit experiment. Now, this is due to the fact that interference only occurs when you have coherent sources of light. Now, what are coherent sources? Two sources of light are said to be coherent if the initial phase difference between the waves emitted remains constant in time. Now, if this does not happen, that means if the phase difference changes as we move along time, then we call them incoherent sources of light. Now, in the Young's double slit experiment, we have a sodium lamp which was kept on the left side, and then from the sodium lamp, light was incident on a single slit, S, and from this single slit, the light will now reach two slits which are of equal distances, S1 and S2. So from both of these slits, the light rays pass across the medium towards the screen, and on the way they hit each other and then interference occurs. So the two coherent sources of light, when they undergo interference, you can see the interference fringes on the screen. And those fringes were captured on a screen, and they consisted of alternate light and dark fringes. Now, because both constructive and destructive interference are at play, areas with light fringes means that they have constructive interference. Areas with dark fringes have destructive interference in them. Now, each of these fringes are something like this. So if this is one fringe, one light fringe, then we will have an equally spaced dark fringe, and then another fringe that is light, and that's the way in which it goes. In interference, all of the fringes have the same intensity. All of the light fringes have the same intensity, and they also have the same width. Now, the width for a fringe in interference is given by the formula beta is equal to capital D by small d times lambda. Lambda refers to the wavelength of light. Since we're using coherent sources from the same lamp, there's only one lambda, and capital D here refers to the displacement between the slits and the screen. So this quantity here is D, and small d refers to the distance or displacement between the slits. So we mentioned that the two slits are actually apart from each other, and so therefore that distance is referred to as d. The displacement between those two slits is d. So in order to find beta, we use the formula capital D lambda divided by small d. This is the distance between two consecutive bright or dark fringes. So if you want to find the distance between these two bright fringes, that means to span across the entire width of the dark fringe, we use the formula d lambda by d. Every fringe in interference patterns have the same fringe width. Now, there is another quantity which we measure called path difference. This is the difference in the distance covered by the two waves. So over here, you have one wave covering, say, A distance, and another wave here covering B distance. Those different distances are different. So the difference in the distances covered by two waves from separate sources of light to a given point P at the interference pattern. This is called path difference, and it is represented as delta phi. And this delta phi for a bright fringe is n times the wavelength. For a dark fringe, however, it is n plus 1 by 2 times the wavelength. Now, based on the interference of light, you can always, find distances on the screen. For example, the distance between the nth bright fringe and the central fringe can be written down as x is equal to n d lambda divided by d. Now, here n refers to the number of the bright fringe. For example, if you want to find the distance of the second bright fringe, then what you do is you write 2 lambda d, capital D, divided by small d, because n here is equal to 2. For the dark fringe, however, it'll be n minus 1 by 2, which we can write down as 2n minus 1 lambda d divided by 2 small d. So that is the distance between the nth dark fringe and the central fringe. So those are the main formulae with respect to interference. You can also study the derivation as well. However, these are the most important formulae that people ask in the exams. The fringe width, for instance, is very important. Also, the path difference could be asked. And the other two formulae, the distance between the bright fringe and central fringe, and the distance between the dark fringe and central fringe, they are asked in word problems and others. So these are applied in word problems. Now that we've studied interference and the Young's double slit experiment, let's look at another another phenomena of light which is explained by the wave theory. And this time we only need one single slit. This is called diffraction of light. So what is diffraction? Now, it can either mean the bending of waves around the corners of a small object, or it could be the bending of waves through an aperture into a region of geometrical shadow. So what essentially happens is that it describes the bending of light as we reach obstacles and gaps which are, comparable to the wavelength of light. So that is how diffraction occurs. In the Young's single slit experiment, we replace the double slit by one single slit, and you can see that they form a diffraction pattern like this one. This is represented in the graphical form, and you can see instantly that in diffraction, the central maxima is more prominent. It has more intensity, the most intensity, and it is twice as wide as the other fringes. And you can see that the formula here is again 2 lambda divided by b. Well, b, or in this case a, refers to the gap, the slit gap. So the slit gap is represented by b. And when you want to talk about angular width, you just add the distance between the slit and the screen, which is capital D. So you multiply that to the width of central maxima in order to get the angular width. So that is 2d lambda divided by b. And for maximum bright fringes, you always can use the formula b sine theta is equal to 2n plus 1 times lambda divided by 2 in order to find out bright fringes and dark fringes. As we move away from the center on both sides, the intensity decreases, and the other fringes will only have half of the width of the central maxima. So those are some of the differences that diffraction has with respect to interference. Now, let's look at the final part of this episode. This leads to resolving power and polarization. Again, some important phenomena in light which we can explain using wave optics. The first is resolving power. Resolving power is basically defined as the ability of an optical system to form distinguishable images of objects which are separated by small angular distance. So that is what we call the resolving power. Now, this resolving power is found in all optical instruments such as microscopes and telescopes. And an important part of the resolving power topic is that it is inversely proportional to the wavelength. So as you can see in both these formulas for telescope and microscope, lambda is always in the denominator. So the resolving power is always inversely proportional to the wavelength. This means that if you have shorter wavelengths of light, such as violet and blue, you get higher resolving power. Whereas if you use red light or say orange light, then the resolving power would get less for the same lens or refracting medium. So for the resolving power of a telescope, we just divide d by 1.22 times lambda, the wavelength. Here d refers to, I guess, the width of the microscope lens. And for a microscope, since the object is forming two or more rays with an angle theta between them, so what happens is that the resolving power is represented as 2n sine theta divided by lambda. Lambda again standing for the wavelength. Next, we look at polarization. Now, in nature, the sunlight that we get, it goes off into all different directions. Here, 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 etc. But in some cases, we want light to go in a specific direction. We want to able to control light to go into a specific direction. So when you can specifically restrict the vibration of light in a particular direction, which is perpendicular to the direction of propagation of a wave, you can say that the light is now polarized. So as you can see here, the incident ray, the incident wave is hitting the surface separating the two media, and then after refraction, you can also find that there is a perpendicular wave which is polarized. So the wave now gets polarized when it is perpendicular to the refracted wave. And next, in order to achieve this, we have a specific law called the Brewster's law, and it says that the maximum polarization of a ray of light may be achieved by letting the ray fall on the surface of a transparent medium like this one in such a way that the refracted ray makes 90-degree angle with the reflected ray. So essentially, it is just a mathematical statement for the polarization that occurs. So in this case, you can find the mu, or refractive index, as tan theta p, where theta p is the angle of polarization. This is theta p. So that means if you have light that is incidenting in an angle in such a way that both the plane polarized light and the unpolarized light are perpendicular to each other, then that angle is referred to as the angle of polarization. And you can always find out the refractive index by finding the tangent ratio of the angle. And in labs, in laboratories, what we in order to analyze polarized light, we use a device called a Polaroid in order to get polarized light. And again, polarization is important because it's used to eliminate the headlight glare in motor cars, and also if you have too much of light, sometimes it may disturb your work, so you use polarization in order to reduce the intensity and the amount of light that is coming to your eyes. So basically, sunglasses, they use polarization in order to make your eyes feel comfortable. So that concludes the chapter wave optics. So in wave optics, we have a lot of derivations, and we also have we are also entering a new stream of optics where we consider light as a wave. So this is basically a chapter that deals with the basics of wave optics, such as how a wave is formed, what are the basic properties and phenomena that is associated with wave optics, such as diffraction, interference, and polarization. And then we talked about coherent sources of light, resolving power, etc. Topics which are related to the main agenda. So that concludes wave optics. We hope you found this chapter interesting. If you want to go back to the earlier chapter, that is ray optics, in order to get into the basics of light propagating in ray fashion, then you can always click the link in the description down below. It leads to the playlist that covers NEET physics syllabus, so mind maps of physics. So you can always do that. And for having more of our useful and interesting content, don't forget to subscribe to our channel, Brain Blitz Audios. So until the next webisode, take care, stay safe, bye bye for now.